freshman year in Project Lead the Way, we learned a lot of basics about designing solutions. And so we learned about the design process, which is something that we've been using all the years after that.
We spent a lot of time modeling, physical models, mathematical models, and also software models. And the things that they're able to do at the end of the first year in modeling just amaze me.
The Project Lead the Way program really taught me a lot of mechanical skills along with electrical and programming, all the disciplines of engineering.
Really, it's about creativity and kind of just having the ability or the willingness to work through ideas and to really get into things and examine what's going on, how does this work, can I make it better, how could I do that, and what are some great ideas that, that might help solve different problems of the world.
We've also learned how to work together in groups and brainstorm, which is something that's really important to do, especially in an engineering career in the future.
It's helped me strengthen my thinking process so that I can go on to college and to these mechanical engineering field and be able to, right out of the gate, know how to think and know how to process things and know how to communicate to other people my ideas.
It's just given me a head start in a lot of the disciplines of engineering that are taught, like mechanical, electrical, and programming. So going into the next step, I'll have a lot of background knowledge about those topics.
I think having background knowledge coming into studying engineering, it's like a big advantage.
The concentration of nitrate will be described throughout this section in units of milligrams per liter. The tests described here are used to measure the concentration of nitrate ions, which is NO3, in water sample.
The lead up from the past 3 years to this year has been the most incredible journey because we've been able to take the curriculum from the past 3 years and use that to become very good at what we're doing this year.
The highlight of the program for me is really this fourth-year capstone course that I'm currently participating in because we get to put all of the skills that we learned in the past 3 years to use in one final project throughout the entire year.
Being in this course is one of the best things academically that could happen to you, second only to maybe getting a perfect SAT or ACT score.
I think that the program has really helped me learn about different types of engineering and lots of different aspects of things that are very applicable to other mathematical and scientific fields.
So you're going to use these tools now that you've acquired to then make more technical sketches. Again, they're not going to be perfect because these are brainstorming sketches. But you're going to use these to move forward.
PLTW has prepared me after Seneca, not only in problem solving, which is a huge thing that we do here, but also in time management.
Being a Project Lead the Way teacher has helped to kind of broaden my world a little bit. It's let me look out into the bigger world and see where science, engineering, technology kind of all come together to solve bigger problems.
Rather than just teaching them how to do something, I find myself thinking about the inherent science and math concepts and trying to draw those out.
I think that my highlight of the Project Lead the Way program is just how much it's taught me in terms of my future career. I've realized that I want to go into an engineering field because of this class.
The things that we got to do in this class were so beyond what we would be able to do in a regular drafting class or really any class you could have taken at Seneca because of the resources that we have.
I think they come out with empowered to be engineers. They understand the fundamentals of what different engineers do and how to use those skills to make things happen.
Ladies and gentlemen, please welcome Lenape Regional High School District Director of Curriculum and Instruction, Mrs. Heather Zanakis.
Thank you all for coming out tonight to this monumental occasion, the capstone project presentations of the Engineering Design and Development Inaugural Project Lead the Way Class of 2018. First, I would like to recognize some of those individuals who made the addition to our program of studies and this night celebration possible. There are many names. I'm going to read them off quickly, and please hold your applause till the end. Our Board of Education members with us tonight: Allison Eckel, Linda Eckenhoff, Paula Lee, Steve Lee. Our district and school administrators, our superintendent, Dr. Carol Birnbaum, Dr. Justin Smith, our assessment, accountability, and planning coordinator, Tony Voro, director of buildings and grounds, Tony Catani, principal of Lenape High School, Joe DeJulius, supervisor of business and technology, Jean Jones, our supervisor of science, and Gary Noecker, supervisor of mathematics. Our Project Lead the Way teachers here at Lenape: Mike Condorso, Jim Scott, Tom Zanakis, and our sponsors: Lockheed Martin, BAE Systems, and our Instant Graphics sponsors. Our partnership team consisted of many people from the community. Some are here tonight: Robert Countess, Dr. Medea Joffrey, Rich Jacobs, Scott Gee, Michael Pfeiffer, Erica Rackow, and Jill Zack. Please give a round of applause to all the people that helped put this together. This journey began in 2013 with a generous grant from Lockheed Martin to support a STEM-related program in our district. And it was the fall of 2014 that Lenape High School began its journey and planning for the implementation of the Project Lead the Way program at our high school. At that time, both Lenape and Seneca volunteered to pilot the program for an incoming 9th grade group of students, these students. There are many unknowns in a first year, like who will teach the first class, Introduction to Engineering Design, who would do that? And what room would be best suited to put both the makerspace design area and the computer workstations, because you needed both? And how would we introduce this idea of Project Lead the Way to the middle schools? After all, we needed some 9th graders to participate. And how would we be able to tell if this was going to be a successful program and a good fit for Lenape High School? And what is unique about this group of students here sitting before you tonight is that during their sophomore year, their junior year, and their senior year, we asked the same questions, again, because they were the pioneers to this Project Lead the Way program at Lenape. Throughout the past 4 years, it has been made abundantly clear that the time taken to discuss, to analyze, and to look critically at the program for Lenape students, that this inaugural PLTW class would pave the way for many students to follow, has been worth it. And we are all looking forward to what the future has in store for these remarkable forward-looking students. And like anything that is new in our lives that we wish to evaluate, we must question and search and refine the process, and sometimes also the product if necessary. And so these students before you tonight have been an integral part of that initial design process, which has lasted for 4 years at Lenape High School, which has led them to this moment, their senior capstone project presentations. And at this time, I would like to turn the program over to Mr. Mike Condorso. Thank you.
So Engineering, Design, and Development is the capstone course in the Project Lead the Way High School Engineering program. It's an open-ended engineering research course in which students work in teams, if they choose, to design and develop an original solution to a well-defined and justified open-ended problem by applying an engineering design process. Students perform research to select, define, and justify a problem. After carefully defining the design requirements and creating multiple solution approaches, teams of students select an approach, create, and test their solution prototype. While processing through the engineering design process, students worked closely with experts to hone their organizational, communication, and interpersonal skills. Their creative and problem-solving abilities and their understanding of the design process Tonight, the students will present and defend their original solution to an outside panel. Tonight's panel includes many people who were already mentioned as part of the partnership team, and also Mr. Ed Cohen of Vision Edge, Mr. Nate Knaus, technology teacher at Cherokee High School, and Miss Vicki Ragsdale from Lockheed Martin. So we appreciate all of your help and guidance as we work through the process here. So I now would like to introduce the students. Presenting first tonight, their modernized violin tuner is Andrew Pye and Garrett Williams.
All right, how is everyone? My name is Garrett Williams.
I'm Andrew Pye.
And this is our final review for the modern violin tuner. So the problem that we found is actually a problem that we have both dealt with personally. I used to play the cello, and Andrew currently plays the violin. And we found that, especially for beginners, the tuning process can prove to be very difficult. Either the students don't know how to properly tune their instrument, or they end up breaking their instrument trying to tune it themselves. So we found that this is a problem, and especially in a classroom setting, it takes up a lot of time, and it really doesn't need to be a problem. So our problem statement was to shorten the time it takes to accurately tune orchestral string instruments.
So of course, we weren't the first ones to try to solve this problem. So here are a few solutions that try to tackle this, the problem of trying to shorten the amount of time it takes to tune orchestral string instruments. So here we have two chromatic tuners that are out on the market, and they simply indicate if you're sharp or flat or you're in tune, and by how much, and therefore you can adjust accordingly. On the left side, we have the Snark tuner, which is a clip-on tuner that uses a vibration sensor in order to detect the frequency that you're playing at. And on the other side, we have a simple tuner app that that utilizes the microphone already inside your smartphones to detect the frequency you're playing at. And you could actually download one of those apps right now, and you can see if I'm talking in tune or not.
We found several other solutions. One is the Rode mechanical guitar tuner. Essentially a device that you place over top the peg of the guitar, and it will listen to the note and correct the note accordingly. We also found the Tronical tuner, which is a built-in tuner that's built directly into the device. It's built into the device, so it's not standalone. It's only for guitars currently.
Okay, so in order to ensure that we were actually solving a problem, we created these guidelines, which are 7 disqualifying specifications, which are things we believe were essential in our product. After compiling data from over 100 people and from surveys who have played the instrument before, gathering data from our teachers and classmates, we decided that we wanted a device that could be completed by the end of the year, that could be built under $250, that could tune an instrument under 1 minute, could accurately recognize a note, play or pluck a device that would not break the instrument or the strings, had enough power to tune the instrument, and could tune at various frequencies.
We also had some additional specifications, and although we didn't need these to get met to complete our problem, or to solve our problem, they're things that we would like to have. So that's the device can firmly attach to the instrument and be removed. It fits a standard size orchestral instrument, can be turned off, is durable, has various software options, is reasonably priced, and has a matching aesthetic.
So in order to understand how our product works and our decisions in creating our designs, I have to briefly go over how a violin works and how you tune it. So essentially, you change the pitch or frequency of the violin by adjusting the tension in the string. And through simple physics, if you increase the tension of the string, the pitch increases and vice versa. So there's usually two ways to manipulate the tension in a violin. First is the pegs, which has the full range of motion, which allows you to turn to any note. And second, we have the fine tuners, which make smaller micro adjustments. Now, after going through 5 designs, we settled on design 3. And this design was unique in that it was the only design that utilized the fine tuners to change the pitch. And the reason why we did that was because we didn't believe we could be able to generate enough power or torque to turn the pegs up here, which are actually, unlike a guitar or ukulele, the pegs on a violin are friction fitted, which means you need a lot more power to turn, while the gears, unlike a guitar, are geared.
So we came up with a decision matrix to come to this decision, and although the design we picked was actually 3rd in our decision matrix, we found it to be the most feasible. Like Andrew said, we felt like we'd have an easier time turning the fine tuners rather than trying to go for the large tuning pegs. And although that wouldn't give us as much of a range of adjustments, they would be more accurate. So here are some concept drawings for a design. We can see it's a very compact design. It fits over the tuning pegs. A motor will turn the fine tuner. A servo will move the motor between the different strings, and there will be an interface where the user can interact with the device. And the next slide. We can see here's a little model of what we were trying to accomplish, and this is a little 3D printed model of what we were going for. And as you can see, we underestimated the scale just a little bit.
Okay, so after we were finished designing our concept, we moved on to the prototyping stage. And here was the rough outline we created at the beginning. First, we wanted to create a motor that would be able to turn the fine tuners easily. And we finally settled on a stepper motor through a long process. The second was to develop a rough hardware system using a breadboard and wires. And in this part, we would implement all the parts such as a vibration sensor, a microphone, servos, motors, etc. Then we would move on to optimize the solution by calibrating the microphone with the actual pitches. And next, we wanted to actually mount the device to the violin. Within the next few weeks, we wanted to adjust the program to turn the fine tuners according to the actual violin notes after calibration. And then for the final few weeks, we wanted to be able to fit everything within a 3D shell and be able to move across multiple strings to tune them. So we developed this working parts list for what we thought we would use in our prototype. This included our microcontroller, which was the Arduino Uno, a breadboard, wires, a battery snap, battery, motors, servos, resistors, LEDs, a microphone, and an accelerometer, which we wanted to use as a vibration sensor in conjunction with our microphone.
So we created a construction timeline as well that goes in line with our incremental testing plan. First, we wanted to assemble the Arduino, get it working, get it programmed. Then we construct a connection between the fine tuner and the motor, because that would be the core part of our device, would be the motor turning the fine tuner. Then we construct a shell for the device, because obviously as a product, it's not good to have open wires and open circuits. So we wanted a shell to keep it compact and protected. And then finally, we would create a mount for the motor to the violin, so you just didn't have to hold the motor. So this is our first iteration. Basically, this is a piezo sensor compact with a motor, and basically the reading from the microphone or the piezo sensor would correspond to the speed of the motor. This was just basically to get us familiar with the Arduino, kind of lay out the framework for our final design. Then we added a servo motor that would simulate switching between different strings. And also we changed the regular motor to a stepper motor. Difference between a regular motor and a stepper motor is that stepper motors act as a servo and a motor. You can tell it a certain speed, or you could also tell it how to turn a certain rotation. So we found that it's a lot easier to turn by the amount of rotation rather than time. Then we added a microphone. This is a lot more accurate than the piezo sensor, and we didn't skimp out on the price with this. We wanted a really accurate microphone to get the best reading possible. And then here, we just continued programming it, we compacted the design, and we started to get the actual functionality for having the microphone listen to the frequency and then adjust the stepper motor accordingly.
So we wanted to compact everything and make it more concise. So we created this 3D shell and made the wiring more concise and put everything into this shell so that it would fit much nicer. And then next we wanted to create something that would be able to connect the motor to the actual fine tuners. That did involve like a bunch of epoxy and super glue. So we decided to use Inventor and create a 3D part. And as you can see, it took a lot of effort. As you see, 3 test plates were used to find the perfect friction fit between the fine tuners and the motor. And in this last iteration, we put everything together. So first, we created another 3D part, which fit over the tailpiece. And as you see right there. And the slits are meant for the Velcro slots. Slots for Velcro that could strap onto the tailpiece to secure the stepper motor. And we strapped the entire 3D shell to the side of the violin on the shoulder rest using Velcro. So our final working parts list was actually a lot less parts than we expected. We were easily under the $250 budget. We ended up using the Arduino Uno, the breadboard, a stepper motor, a servo motor, the Adafruit microphone, 3D printed components, and wires. And this amounted to about $50. And while this was a lot less than our budget, we could definitely get this price down to even like $20. As Arduino was quite overpowered for what we were using, we could easily find a microcontroller for $5 or less to finish the same task. And with more time, we could implement the solution on a PCB board with soldering, and so we could eliminate the need for breadboards and wire.
All right, so in the interest of time, we're going to skip the video. We're going to go right to a live demonstration, and I'll kind of explain it.
Okay. Ooh, okay.
So basically, we're just going to show the device working as is. Hopefully, we don't pull an Apple here, and hopefully it works correctly.
Yeah. Yeah, so the video was collateral for the live demonstration doesn't go wrong. So we'll see. Okay, so right now, we were only able to implement this solution on one string due to time constraints. So everything I'll be playing will only be on the A string. So just take my word for it, I promise. So right now I'll play what it is. It's kind of out of tune, as you see. It doesn't sound good. So now I'm going to plug it in. Tell the pitch is slowly changing, the motor is slowly turning. And it turned a little bit. I think it was not that out of tune. So now I can play. Okay, so we'll now see the results.
So this is just an example from our code that the readings we're getting, what the device is doing. It's reading the microphone, it's getting the microphone readings and then adjusting accordingly based on how off it is. And then here we just have our test. We found that it was an average accuracy of 1.2 hertz, tuned in about 38.484 seconds, and we didn't need to interact with it, and there was no damage to the instrument.
So if you remember, I stated a few disqualifying specifications at the beginning of the presentation. And at the end, we met most of these criteria. We were able to complete the device by the end of the year. We were able to build it under $250. We were able to tune it under 1 minute and able to accurately recognize the note, pluck or play with the bow. Also, so far, the device has not broken the instrument or the strings. And so, however, the other two criteria we did not meet. For the criteria, the device has enough power to tune the instrument. We did not meet because while we were able to easily turn the fine tuners in our product, we weren't able to change the pegs, which was our end goal. And the other criteria was the device that can tune at various frequencies. And the problem with this is because the standard at which instruments are tuned around the world is a bit different everywhere. For instance, in the US, the standard A string is tuned to 440 hertz, while in Europe, it's 441 hertz. But however, unlike our previous criteria we did not meet, which needs like new battery technology or motor technology to achieve, this criteria could be easily achieved with a bit more time.
All right, so what we learned from this experience, we got the device to listen to the note and then adjust accordingly, and we also got it accurate enough to not break the instrument. Where we go from here, we want to add functionality to move the device across different strings, make it faster, and make it more accurate. And finally, a big thank you to all of you for coming out tonight, especially to the engineers on the panel. We really appreciate your feedback. We wouldn't have gotten this far without you. It helped us limit our scope and come with a completed product.
Thank you, Andrew and Garrett. Well done. I'd now like to introduce the Lift Buddy group, consisting of Nathaniel Kim, Jonathan Landis, and Keval Tassani.
Hello, my name is Keval Tassani.
I'm Jonathan Landis.
And I'm Nathaniel Kim. And this is our final presentation, Lift Buddy. So how we got started, we started off the year trying to come up with a design to automate the spotting process for the bench press. We soon found out that we would not be able to accomplish that by the end of this year. Then we moved on to working with trying to keep statistics for the benchers. And then we eventually switched to working on our way to detect whether a good or bad repetition has been performed during bicep curls.
So our problem statement, many people who perform bicep curls in the gym do not perform good solid repetitions and proper form, and this puts them at injury risk. So before coming up with a solution to the problem, we had to come up with some of our design goals that our solution will entail. The first is that it needs to be able to provide feedback to the user. So to do this, we're going to have working LEDs, and we're going to have red and green LEDs to signify when the proper distance has been completed. So when performing a bicep curl, the distance from your wrist to the shoulder, the smaller the distance is, the better the repetition has been. So the LEDs, when the green LED lights up, it signifies a better repetition. The second goal we had is that it needs to be able to provide an exact distance. So to do this, we're going to need to use the ultrasonic sensor, which can signify a change in light. So when something comes in front of the sensor, such as the shoulder, it will signify that the distance that will be read, and it will appear on a computer screen nearby. The final goal we had was that it needs to be portable. So we're going to need to condense the size of the design so it can fit comfortably on someone's wrist, because if it's not comfortable, there's no point, no one's going to want to buy it, and they're going to need to have comfort level while working out.
So our proposed solution was that we would have a breadboard for the wiring. Then we would attach the ultrasonic sensor to the breadboard, and by using different wires, we will connect LEDs to the ultrasonic sensor, and we would have one red LED and one green LED. We would also have a screen to display the data and statistics for the user. And so this is just like a rough sketch of one of our first drawings. On the left, you can see the breadboard with, on the top left part is like an ultrasonic sensor. On the right part of that, on the left side, is an Arduino. So that's what we use to like connect, and that's how we're going to use for the coding.
And then the possible casing would be on the right side. So there'd be like the breadboard there and then the Arduino right next to it. So that way it's all compact and together.
For the solution justification, we will show a good repetition based on the LED color. So a good repetition would show the green LED, while the distance outside of the restricted distance would show a red LED. And it would be able to read the distance from using the ultrasonic sensor.
So this is like a test rod.
So while performing this repetition, the red light signifies bad rep until he's 12 centimeters away, which shows the green LED turns on and lights up, and signifies a good rep to the person working out to perform the bicep curls. And as you can see, as he finishes 12 centimeters green light, that goes back to red throughout the rest of the repetition.
Originally for the casing, we had this design, but after we 3D printed this casing, the breadboard did not actually fit, so we had to move on to just encasing the ultrasonic sensor, and we would eventually get rid of the breadboard and solder all the wires together to create a more compact design.
So as Nate mentioned, we soldered the wires. So as you can see, for all like the wirings that we had to use the solder to make sure that the connection would stay good. And this helped eliminate the size of our product, because our product was very large before, but now with the use of soldering, we had it all compact, and we could also eliminate the use of a breadboard, because all of it would just fit right onto the Arduino.
So the most important part of our design was the coding, and none of us are really skilled coders, so dating back to our original problems, we had to start learning how to code in Python because we had the Raspberry Pi Zero, and Python was the language that was compatible with it. So we were using the website Code Academy to learn how to code Python, and after doing this for a while, we were unable to download the software onto the school computers, so we had to switch to Arduino. And we found it to be much more user-friendly, and we previously worked with Arduino in the class before, so it was much more effective, and we were able to transition smoothly into Arduino. And here is some of our coding for our product. And at the top left, you can see the number defined. We had to define all of the 4 variables for the ports that we use, such as trig pin, echo pin, LED 1, and LED 2.
And then another main part of our code was this, if the middle part, the if distance less than 12 centimeters. So that is signifying the distance between the wrist and the shoulder, which will be the good rep. So if it's less than 12 centimeters between the wrist and the shoulder, then the green LED will turn on.
And we also had to change the centimeters in the bottom from inches, because that's the website we got off of. So the most important part to test our product, knowing that it works and everything, we have to test it. We're using outside people. And so this is our testing procedure. The first step is to set up the wiring with the Arduino Uno and the breadboard. And we use the website called instructables.com. And the picture in the top right corner is off of that website. So we had to match all the LEDs, resistors, and wires perfectly, as shown in the picture, to get it to work. Next up, we had to use Arduino 1.8.3 program, which is located on the school computer, to set up the coding, which was shown on the last slide. We then had to connect the Arduino with to the computer using the USB. And then we placed the casing on our wrist, and with the ultrasonic sensor facing the shoulder so that it could sense the distance between them. And we had the testes put on a blindfold, because we didn't want them to see the light changing color, because if they saw that, they might keep pushing their reps even closer to get a green light, because they could tell that's good. And we didn't want them to do that. We wanted it to be a normal workout, so there was no bias in the results. And then obviously the last step is to begin performing the bicep curls. So we had each person perform 3 sets of 10 repetitions to act like a normal workout, to simulate a normal workout. And we gave them 30-second breaks in between each set, so they would be able to replenish their energy and get ready for the next set. So basically we would count how many good repetitions were performed based on the green lights, the amount of green lights that lit up. And we would ask the user how many good repetitions they thought they performed, and we compared the 2 numbers together. And we would also record the amount of weight curled.
We had the 3 people who tested our design perform 3 different sets of 10 repetitions, as John said. And we had them use their normal weights for their bicep curls, which was either 20 or 30 pounds. And after each set, we asked the participants how many good reps they thought that they had. And we then compared this number to how many our design actually said that they did. And about 50% of the time, the person thought they performed more good reps than the true number they actually reported. And this was our testing results. For the trial numbers, those were each of the 3 participants that we had.
So the project objectives was for the user to get feedback from the ultrasonic sensor, be able to read the exact distance between the wrist and the shoulder, and be portable so that when they bring it to the gym, they don't have to lug it around. It's just something that they can have in their pocket, pull it out, put it on their wrist, and perform their workout with ease. So these were the 3 objectives, and we were able to hit the portability, reading exact distance, but we were not able to hit the giving the user feedback on a screen.
This was what we came up with. We still had to finish the casing at the time, and yeah.
So if we were to bring this to market, our first thing would be to sell direct to the user through an online store. And then we would try to expand by going into gyms, and the gyms have like different stores within them, so we would try to like market it to the gym owner to see if they can get our product in there. And we believe that a price point of around like $25 would be a good price for this type of product, because it's not too expensive with the materials, because it's just the LEDs, the wires, and the Arduino. It shouldn't be too expensive. But this price point is also reasonable for like the user to buy. They won't feel like they're breaking the bank when they're trying to get this product.
Our future plans, we had planned to install a built-in screen which displays the information for the actual user. And we would have this device work for other exercises. Right now we only have it for the bicep curl, but we plan to have it for the shoulder extensions and also bench press. We would construct the housing for all the components, including a wristband that would make it comfortable for the user while they're performing their repetitions. And we would add other functions, such as tracking the history of data for each user.
Thank you for your time. We'd like to give a special thanks to Mr. Condorso and the PDR and CDR panel. Thank you.
Well done, gentlemen. Thank you. And presenting next, the Animated Turf Group, consisting of Joseph Cornaglia and Brett Gallagher.
All right, how you doing, guys? I'm Joey Cornaglia.
And I'm Brett Gallagher, and our project was Animated Turf. So our problem statement was to make turf fields more versatile and easily customizable for sports use. So to explain that a little bit more, our vision was to have turf be able to display images, logos, and lines on the field in real time, similar to as you see here on a basketball court, which is just used from a projector. But we wanted it on a turf for like a football field or lacrosse or something.
So for our justification, we had to decide whether we wanted to use a real grass field or a turf field to modify. And we found that with the growing turf market, especially in the NFL, and that it's easier to maintain because you don't need to like repaint it or cut it or anything, that a turf solution would be better because it's permanent.
So some current and past solutions. The first one was stencils, which the NFL uses on grass fields, but they take a lot of time and they're not easily replaced. Also, there's field liners for like baseball when you do the foul line, and it requires a human to do it and could be messy and have human error. Then there's a line drawing robot, which takes a while and it makes permanent lines when we wanted it to happen in real time. And then there's also color turf, which has many lines on it, which can be confusing, and you can't really change it.
So we had a bunch of alternative designs, and although we're not going to get too far into them in this presentation, this is just the decisions that we made when we selected ours, and the solution that you'll see next is what we deem to be the best. So this was our original design. It's just a grid of LEDs that would then go under the field, And then to shine them through, as you can see in the bottom design, the LEDs feed into fiber optics, which bring the light up above the grass so you can see it.
So when we got the initial supplies, we messed around with like fiber optics. So this is an example of N-Glow fiber optics we used on just a simple LED. And then we could have chosen N-Glow, which they just come out the end, or Side Glow, which comes out all throughout the fiber optic. We went with N-Glow because we felt it would be better to just come out the tip of the grass instead of the full thing.
And here is an early version, just when we had one light to get the electronics sort of going. Excuse the audio there. But that's just the light changing colors, so we can learn how to do it. And then for our next iteration, we had all of the lights controlled off of one pin, which was one of our specifications. So that's 240 lights on a strip, all being controlled from one control pin on the Arduino. And then we had to integrate the fiber optics. So we used the laser cutter, and this is the CNC machine, to make a bunch of holes in a plastic board, and then that attached to the bottom of the turf sample we have, which you'll see at the science fair. And you can see that the fiber optics would go through that and through the turf.
So here's an early prototype that we had. And it's just one row, and this is before we integrated the board, so the fiber optics is just going through one of the boards and through the turf. So then, as we got further along the prototype, we added another board underneath for the LEDs, and then we connected straws to the LEDs to hold the fiber optics in place, which then go through the board and the turf together. So then here's all that into the full prototype. So the LEDs are on the bottom, connected with straws, and they go through the turf with the fiber optics, and they can just change from the LEDs.
All right, so one thing that we wanted to do was definitely be able to get specific graphics into this. So a fitting one we chose would be the Lenape L. And to do this, you need an array of each color for each light. So this would be really hard to do manually. Thankfully, we found a piece of software here that can convert the pixels into the arrays, which you can see here. But there was one issue we ran into, which is that when we wired our LEDs, they go back and forth like a serpentine. And that program converts it so it goes straight. So in order to do that, we just made it backwards, but if it was a larger image, there's like 6 lines of code that you can just reverse every other one. So that fixes that. So our first criteria for our specifications was that the turf is able to change color in specific positions, which means we can control all the lights. So in the next slide, you can see that's the Lenape L without the fiber optics. And then that's how the fiber optics carry the image through the turf.
So our second criteria was that it wouldn't inhibit athletic performance. And we didn't fully test this, but right now the fiber optics are like the same as the turf, so we don't think it'll have like any obvious signs that it'll inhibit athletic performance, but we didn't fully test it yet.
We didn't want to stomp on it before we got to show you guys what it could do. And then our third criteria is to be easily visible to spectators and players. This is hard to judge because our model is only 11 inches by 11 inches right now. Although we think that it's a pretty good visibility, we think it could be better. So we think if we made a Mark II, we would have thicker fiber optics and probably more densely packed lights and fiber optics.
We also wanted it to survive normal turf conditions such as heat, impact, and weather. So we did not test on the impact because we did not want it to break right before the presentation. And then waterproofing it, the LEDs are the only thing that are not waterproof, but you can easily just get waterproofed strips. And then we did not test for heat. We did not want to break it before the presentation.
Criteria 5 is that it would be allowed in the NFL if we ever got that big that we could sell it to them. Although there's nothing disallowing it from being in the NFL, there hasn't been proposed to them to our knowledge, so there's no rule saying you can do it.
And then we also wanted to finish in the school year. So in the future, we want to complete some of the testing, integrate more lights and make it bigger overall, and then integrate the waterproofing.
And criteria 7 was that we stayed within our $250 budget allowed by the school, which we did. We spent $20 for the turf samples just for shipping, about $100 on light strips, and $45 for various fiber optics, most of which we didn't actually use because we were just testing them out. Thank you very much for coming out and all the help, guys.
Thank you, Brett and Joey. And presenting the car cooler next is Zack R. Levitt.
Hello, I'm Zach, and I'm presenting the car cooler today. My knowledge of the marketplace, I found that cars left out parked in the summer get really hot because of the way the sun's light gets trapped inside the windows, and it heats up really fast and can cause heat death if someone is left inside the car, be it a pet or a small child, from possibly irresponsible people. It's also very inconvenient to get into your car and realize it's searing hot inside. I found a few previous attempts to fix this problem. They revolved around doing insulation and car battery going to a cooling system, but they were never fully sold or implemented as devices on their own. The main design requirements is that the solution should be able to prevent vehicular heat death, which happens at around 107 degrees Fahrenheit. The solution should be able to function at all times when the engine of the car is off. And the technology required to implement the solution does exist or can be made within the time frame of the school year. Additional requirements that weren't necessary to be met but would be nice to meet was that it's an original idea. It is very cheap to make, from $20 to $40. It doesn't impede the driver's view of the road or the surrounding vehicles. The solution will be easy to fix and reliable. It'll be able to be applied to most cars and trucks regardless of model or make. And it'll be weather resistant and leak proof. These are just some design concept generations that I had. The class review and decision matrix ruled that concept 2 was the one that I went with, so I chose it. Concept 2 and 5 seem to be investable, didn't have to rely on outside power, self-made. Chose 2 over 5 because 5 would slowly overheat anyway. The solution I chose is a design featuring a solar panel that goes to a battery, and it powers a thermistor circuit, which is linked to a fan, and when the temperature of the circuit reaches a certain amount, it triggers the fan to turn on, but until then the solar panels just charge the battery. The ethics of it, that it wouldn't violate any sort of regulations. The development would just be from the oil cracking and manufacturing for the plastic of the device parts. And the benefits far offset the negatives by saving possible lives. Some developmental work I did. Early in the testing, I had 2 separate fans tested. I went with the smaller model because, believe it or not, solar panels can't provide that much constant energy. So here we have the demonstration of the concept. I had it set to activate the relay once 35 degrees Celsius is reached on the thermistor. 35 degrees Celsius is about equal to 95 degrees Fahrenheit, which you should probably know is very uncomfortable in a car and is approaching heat death. The models in the image, the one on the left is inactive while the one on the right has reached the trigger temperature and is turned on. Here is my wiring diagram, what I planned it to be. It's a simplified map of the finished prototype. So the big idea of applying the fan to the car, I needed a way to attach it to the window, so I came up with a 3D printed duct that I would apply to the window, and it would have these little jigsaw parts that would go around the window as it slides up and would hold the fan on the door so that it wouldn't be letting too much air in or weather. The openings on both sides were made to have similar amounts of surface area so that it would have a decent amount of airflow. This is me putting the device onto my car. Well, not my car, but I hope to have a car soon anyway. There's 2 solar panels that were needed to power both the thermistor and the fan at once. They are up on the back shelf of the car. It is an ideal spot for it. As you can see, you have the duct stuck onto the window with the fan on it. My test criteria was that the device would be able to prevent vehicular heat death. If the cabin of the car reached this temperature, the passenger may die, and that the device would be able to work when the engine is off. Currently, the prototype I have does not prevent rain from getting in, though I hope to improve this shortly. What I do have done, however, is pretty much all of it. As you can see on the test data, the control variant is the car without the device applied to it. This was done over a full hour. I took a recording of the temperature every 5 minutes. And the experimental is with the car that has the device on it. As you can see, the one that has the prototype working on it, it reached the trigger temperature and then the fan made sure it didn't exceed past it, therefore preventing the heat death. That's pretty much what I said. External evaluation that I've gotten from previous things have been incorporated. The main points I found is make the device 24/7 applied rather than situationally. Currently, it is able to be like that. It is not weatherproof yet, and the fan can be applied to the window, which was a major question of previous presentations. I believe I could have been sooner to develop certain components, such as the 3D printed duct, but overall the project went very well as I accomplished the main goal of it I set out for myself.
Thank you, Zach. And next presenting hands-on learning for young kids is Julia Zack.
Hi everyone, my name is Julia Zack. My project is titled Hands-on Learning for Young Kids, and this is my final design presentation. So this is my problem identification and research. So the problem that I wanted to address was that with the abundance of today's electronics, many young kids are learning through phone apps only. Unfortunately, kids learn better hands-on, so this is resulting in poor development of social skills, motor skills, and independence. So my revised problem statement is to give toddlers and preschoolers in the U.S. a fun, effective, and hands-on way to learn letters and/or numbers, opposed to only learning using touchscreen devices. So this is some of my problem research that I wanted to touch on. I conducted a survey of parents of young children and people who work with young kids, and 94% of my respondents stated that they think young children spend too much time on electronic devices. Studies have shown that this can cause brain damage, and screen time for children under the age of 3 can cause issues with learning math and science, and it can impair their development of motor skills. This is some of my market research that I wanted to touch on. So this is a phone case that the kids can play with while they're learning. This is called the Leapfrog Scribble and Write, so they can practice tracing different letters. And this is the Leapfrog LeapPad, which is like an iPad for children, so it's only child-friendly apps and learning tools. So this is my solution. These are the design requirements that I identified. The design must be safe for children under the age of 5. That's the most important. It must help children learn a concept by being able to repetitively practice a skill. It must incorporate hands-on learning, which I defined as learning while using fine motor skills, manipulating objects with multiple textures, or moving. It must be engaging, as well as durable and long-lasting, and of course it has to be able to be used easily by children of this age. So my chosen concept I kind of refer to as electronic hopscotch. So the idea is that there is an auditory output, and it will tell you what letter or number to go to. For example, it will say go to number 3. And there's different tiles, and they have different numbers on them, and the numbers switch between different tiles. And so number 3 would light up, so the kid would know which tile that they're supposed to go on, and then they would jump on it, hopefully the correct tile, and there's a pressure sensor in it, and so the system will know which tile they're on based on the pressure sensor. And so there's an auditory output and a visual association with the numbers and letters. So the justification for my concept, it was the most feasible out of all my different concepts based on my skills and time constraints for the project. It allows children to associate what a number or letter looks like with what it sounds like, which is very beneficial for learning. It gets children moving, it's engaging and durable, and it's safe because all the electronics components are contained within the heavy-duty tile. So this is my revised parts list. I have 2 large 7-segment displays. I initially planned on prototyping 2 separate tiles, a shift register, which according to my research would make it easier to code for a 7-segment display and wire it together, and 2 pressure sensor switches, an Arduino, springs, wire, and a power supply. So this is the process of how I created my prototype. So first I created pseudocode. First I had to set up everything and define all my variables for the 7-segment displays, and then I had to get it activated by a button, so when a button was pressed, it would turn on the code, and it would switch randomly between different letters and numbers until the button was pressed again. So first, I created some different circuits, breadboarding using Arduino to practice. And then I created a simple code in Arduino, which kind of turns on and off a light, so I could familiarize myself with coding for Arduino. This is a wire diagram for a circuit that I found while researching. So I ultimately decided to breadboard a small 7-segment display instead of using the large ones I ordered. In addition to that, it required too much power than we could easily access. So I decided to use this instead for my code. And so this is a picture of my final circuit, and you can see the button on the left and the small 7-segment display on the right of the breadboard. So first I had to get it to switch between different letters and numbers in order. So I built the circuit, I found a code online that did this. It kind of was for testing a 7-segment display, so it showed how it would sequence through each number and letter. And there were some errors with this, so I had to switch it from common anode to common cathode, which corresponded to the LED 7-segment display that I was using. And I had to correct some wire placement, which was incorrect. So here is a video of it switching numbers and then letters in order. So then next I had to get it to do that randomly. So I did some research on random numbers in Arduino, and I created and tested a code that would just generate a random number. And once I got that working, I had to implement that into my other code. And so the idea was that I would have the computer generate a random number, and then I would assign it to a case. So there were cases 0 through 15, which corresponded to the letter or number output on the 7-segment display. So that was how I was going to get them to change randomly. And I also wanted to note that this is a pseudo-random number because computers cannot accurately generate a fully random number. So this is a video of it switching randomly. It's a little slow here, but we edited that so it switches faster. And then finally, I had to get that code to be activated by a button. So I used an Arduino book to create a button circuit on my breadboard. I modeled different codes that would activate and deactivate a code when the button was pressed and pressed again. This was simple things like turning on and off an LED. And so when it came to implementing that to the code I had already been using, it was a little more difficult. So I had a mentor help me create a more complex code that would do what I wanted. Here is a video. So I press the button and it turns on and the numbers start switching. Press the button again and the LED goes blank. So in terms of testing my code, I first wanted it to be able to I wanted to make sure that the code was activated successfully with a button press, and then it had to switch the numbers randomly at least 4 times after the button was pressed, and then the code had to stop when the button was pressed again. So I tested it 3 times and it passed each time. Here are some notes from my code testing. The button was a little touchy, so if it was not pressed squarely and quickly, it would not register that it was pressed at all. And all the wires had to be in place and not touched during this for the button to accurately be sensed. And there is a transmitter LED on the Arduino. It's labeled TX, and when the button press is sensed, that would light up before the LED would respond. So this is the process of how I came about prototyping my tile. Initially, this was going to be integrated with the code, but because of difficulties with the large 7-segment display, it is just for durability and proof of concept. So this is my inventor drawing. My final product ended up being very similar to this, except for a few dimensions. Here is a technical sketch. My final tile was a little bit smaller. So the layout I changed a little bit. I decided to have an electronics case wired outside of all the tiles. Before I was going to have a common base where everything was wired under it, but this would better protect the electronics and it would keep the tiles thinner. So I thought this was a better solution. There are standoffs that support the springs, so it protects the inside parts in case the springs would be depressed too much, nothing gets crushed on the inside. And it also adds, it keeps some of the weight off the spring. And I created this out of plexiglass, which I sanded in order to hide any scratch marks that may occur. So to create my prototype, I first cut the top and bottom pieces, and then I laid out the inside, which was the large 7-segment display, and I put a mat under it to protect the electronics. I made sure everything fit, and then I measured the standoffs, and we cut them and welded them using acrylic solvent. And we had to create a special standoff for the buttons, so when the tile was depressed and it was standing on all the different standoffs, the button was also depressed. And then we attached the springs and had to make sure that the button was actually being pressed all the way and it was registering. So we tested the continuity of that using a multimeter. So I stepped on the tile with the springs and it worked. And then I cut the top box, which I refer to as like the side pieces. And there's kind of a top piece that's open where they're being stepped on, so it kind of holds everything together. And then I welded that together. So these are pictures. On the left, it's the top and bottom piece attached with springs. You can see the white 7-segment display in the middle and the blue mat under it. And on the right, that has the side and top pieces attached, so that's the final tile prototype. So then I tested it. Ultimately, I planned on testing it more rigorously than I did, but the plexiglass was not as strong as I anticipated because I had it cut into small pieces and welded on thin edges. So I decided that material wasn't sufficient, so I didn't want to break my only prototype. So I tested it for durability in terms of the things on the inside and making sure they were all still functioning. So I made sure it functioned after a person weighing between 90 and 110 pounds stepped on and off it 25 times. It passed, but the person that was stepping on it noted that it seemed a little wobbly to step on the top piece. That's something I wanted to improve. And it had to function after being dropped from a height of 1 foot 10 times. After 7 times, the bottom piece where I welded it to the side piece started peeling off, so I stopped dropping it. And that was obviously something that needed fixed. So in terms of improvements, I would obviously change the tile material. My teacher suggested using blow molding plastic, so there wouldn't be any different like small edges that were attached together, and it would be durable. I would like to add more springs to the design, so it would be able to hold more weight and it wouldn't be as wobbly or uneven when it was stepped on. And I would like to implement the auditory output and the idea of it being the correct tile, the correct button that is being depressed when the right tile is being stepped on. Special thanks to these people who helped me throughout my project and after school and on their own time. Thank you for your time. If you have any questions or comments, please come see me at the science fair. Thank you.
Thank you, Julia. Well done. And presenting Resisting Overexertion next is Sanjana Jampana and Niveditha Ramalingam.
Hi everyone, thank you for coming out this evening. My name is Nivi Ramalingam and this is my partner, Sanjana Jampana. And today, before we get into our problem statement, I just want to give a little background about why we chose this specific problem. So I've been an athlete since 5th grade. I play tennis, and I'm not very good, but I still play. And sophomore year, I accidentally hurt my foot and was out it for the whole season. Now, the main reason was because I didn't really realize that, and I kept playing. I kept going for, I think, 2 weeks before my coach finally sat me down and said, "You're done." And so that's why we decided that overexertion is really quite a big problem, and that's why we wanted to tackle this problem statement: to monitor load and acceleration, to address overexertion in high school athletes during athletic activity.
So in order to actually get into what we wanted to address and what we wanted to get going with for our year, we really had to justify what we were doing. So there are a couple ethical justifications you had to consider especially like what group we had to focus on. So we decided on high school athletes, such as Neve, people who would really benefit from a solution like this, and people who are injury prone and would need something to help them overcome a problem that many high school students face today. Also, we needed a solution that serves to prevent overexertion and one that is safe to use. So we did a little bit of research. Some of you who came to our preliminary design review and critical design review may remember this, but one of the major things that we found is that a lot of time is lost for students who suffer from overexertion and therefore get an injury. And we also looked to some experts to really see why we needed to go in the direction that we did, and a couple professional opinions on the topic said that medical tech is the way to go with addressing problems such as the one that we are today. So we really thought this was a good idea.
So before we could actually get into building our prototype, we had to choose a specific solution. And we saw throughout market research that we already had existing solutions. For example, there are a lot of apps out on the App Store that are meant to help encourage you and try and coach you through running, but it does nothing for preventing injuries. The most similar design to what we had planned was the Digit Sole. It's basically a shoe insert that goes into your shoe and is meant to track your movement and warn you when you may be on the risk of injuring yourself. So to develop our solutions, we came up with specific design specifications, parameters, and constraints that helped us decide what we would want to tackle. And some of the most important ones were that it needs to meet, first of all, the consumer's need to accurately monitor and assess the health. It needs to be able to comfortably integrate into sports gear so that the athlete can use it during exercise, and it needs to be both durable and water and sweat proof for at least 1 year. We came up with 5 design ideas, and after looking at a decision matrix plus feedback from classmates and other people, we decided to go with design 3, and this is a little sketch. As you can see, it is very similar to a shoe insert. We intended to have pressure sensors that would monitor, and if it detected that there was too much pressure on a certain part of the foot, you would get a warning through an app that would be connected. However, we decided that probably wasn't a good idea after feedback, and our most recent solution, this is a small sketch, is that you would clip something into your shoe, and you would have the circuit board to take into account how much resistance your foot was showing.
So finally we got to the point where we could finally construct our prototype. So for those of you who saw it before, we actually had an original prototype design that we formatted in CAD, and although at the time we thought it was a really good idea, we came to the conclusion that the proportions were really out of the place and there was a lot of changes that needed to be made, but with the encasing, and with the encasing at the top, there was a lot that we thought would be good and that we should keep for our final design, which you'll see later. So we edited the design to include pressure sensors that could be used to track what's going on down at the foot, and it turned out to be a very bulky solution with everything that needed to go into it, and we decided to scrap this idea and revisit the drawing board to figure out what we needed to do from here. So with the materials that we bought, we ultimately only had to get the light blue beam plus, which is the circuit we use to control everything, as well as a flex resistor, which we'll talk about a little bit later, which is used to record some of the data, and everything else was available to us through family, friends, or the classroom. So we followed a 4-step process in our timeline, along with our incremental design, or incremental timeline. And the first one was to gather the materials, as we showed on the previous slide, then to also assemble the circuit that we had, and then design and print the 3D encasing that would house everything that we have assembled, and then fit everything together for that final bit of integration that we needed, which is where we are at today. So these are a couple of the technical drawings that we drew up for the 3D modeling that was involved in our final design. So this is the encasing, which is very similar to what we had before, although it looks simple, it's very effective for what we needed to do. And then for the clip, that actually goes on the shoe and houses both the wires that connect all the materials together, and then also is in a position where it is comfortable for someone to wear. So this is our final construction. This will be available at the science fair to see if you come by later, but ultimately on the left, that is the box encasing. The red part is the clip, and the flex resistor is the one on the bottom.
So there was a lot of behind the scenes work that went into this, known as coding. And this video just shows how we managed to establish a connection between the Bright Blue Beam Plus, which is our microprocessor, and our computer where we would code. So this is an app called the Bean Loader, and we basically downloaded it onto the Mac, and this app is specifically made to help establish that connection. From there, we could code in Arduino. So one of the first things that we did was we found accelerometer readings. The Bright Blue Beam Plus already came with one built in. And basically this means that we were able to get X, Y, and Z coordinates at any period in time, depending on how this device was positioned. So here's just a quick video on how we were able to do that. In the background, we have the Arduino and the code. And we pull up this Bean Loader where we would connect. And then we opened up the Bright Blue Beam Plus. It doesn't really connect with the serial monitor, so we weren't able to establish that. However, we did open a window in the terminal, and those little dots you can see on the black screen are the readings we were getting about every 5 seconds. Next, and what was probably the most important part, was the flex resistor readings. We had a flex resistor connected, and it would find both the resistance and the bend angle. And the idea was that if your foot bends too much, this flex resistor would be able to tell, and we could give out a warning to watch it. And this is the code. Basically, the readings was pretty similar to how the accelerometers worked.
So after we had constructed everything and assembled the code, we did a little bit of testing. One of our key tests was the connection test. We had two components to it, one for the accelerometer and one for the flex resistor, which are both of the sources in which we are gathering data. So the criteria that we really had to meet was that the Beam Plus is still running after 4 hours, that accurate information was being transmitted to the serial monitor and for the sketches, and then also specifically for the flex resistor, that from 50 yards away you could still get accurate readings. So for the accelerometer test procedure, we had the circuit moved into 4 different positions at 0, 90, 180, and 270 degrees. And we moved it to in those different positions and tested it a few times around to see if the data was accurate. So from our test results, we saw that it was really accurate. As our expected thing was 0, 90, 180, and 270 along the x-axis. We saw that there was only a light bit of variance between that and what we actually wanted, and that could be sourced to maybe a little bit of hand movement or slight human error in holding the actual device, which is very minimal. And that same pattern followed with the y-axis data, which is very close, and the z-axis data as well. So for the flex resistor, we had to bend it to a certain angle and then move it from the 1 yard position right by the computer where we were testing to 50 yards away to see if that data held and that it was reading accurate information. And from our testing, we saw that that was happening and that there was very little error in what we were getting, and that it was accurately doing its task.
Okay, and then our last test was to test that there was a viable kill switch in case something malfunctioned. And the Bean Loader already has a sketch for that called the stop sketch. And so basically what we did was we turned on an LED that the Beam Plus has and had it running for a couple of seconds, and then we would command it to stop the sketch, and if it did within a 2-second period, as you can see for all 5 trials, it was deemed successful.
So we would like to reflect a little bit upon what we've done, and we really consider the project recommendations that we got from our preliminary design review and our critical design review panels. So we wanted to develop a more durable and comfortable design, which we did through the clip that fits comfortably within a size 8 shoe and could change proportionately for different sizes, something that we saw from one of our preliminary design review members. as something that was very important to address. And we also wanted to make some improvements in the future in the last couple of weeks that we have, and perhaps in the future if we want to make this an idea that we could patent or something like that, so we could readjust the design and figure out how to display an error message so that people are effectively warned about what's going on, and they can actually use this device to help them in many ways. And also to maybe incorporate more sensors so more is really being taken out of this design, and a lot of people can be benefited from this. And we'd like to thank everyone on our preliminary design review and critical design review panels for all the feedback, the tech ed department for giving us all the support through all the after-school sessions and everything that came into this, and specifically to Mr. Conderso, Ms. Rocco, Mr. Scott, Mr. Smith, and Mr. Sicilianti for helping us a ton throughout everything we've been doing. So thank you, and catch us at the science fair.
Thank you. And our final student presentation for the evening, Jackson Bauer and Sean Baricca will be presenting lacrosse goalie training.
Hi everyone, my name is Jackson Bauer.
And I'm Sean Baricca.
And today we will be presenting to you our solution to a problem we identified that was lacrosse goalie training. So a little background on our problem is that lacrosse goalies, along with goalies in other sports, but specifically in lacrosse, they have a hard time practicing by themselves. So if you think about it, someone else always needs to be there taking shots at them, and so they can't practice on their own. They can't take shots on their own and practice blocking them. So what we wanted to do to solve the problem was to create something that would allow the lacrosse goalkeepers to practice saving shots in a realistic game-like environment at any location at any time.
So with this problem statement, we had to prove that this problem is valid, and we found that lacrosse is the most rapidly growing sport in America, so that's a very big market for the future and now, and that we, on an online survey with 57 responses of people familiar with lacrosse, whether through coaching or playing, that 61% of them are willing to pay up to $300 for a lacrosse training device, and a third of them are willing to pay anywhere from $300 to $600 for such a device. So to solve our problem, we started to generate concepts. We began with brainstorming. No idea is a bad idea. We had upwards of 12, I believe, and then we narrowed it down to 5, and then again down to these 3. So here we have a ball shooter, a moving wall, and what we chose, the video game. And to choose this, we used the decision matrix, and we judged each concept that we developed. This is our top 5 on specifications we felt were necessary to have an effective design. And if it was a disqualifying statement, it was weighed more heavily, and then we progressively went down, and each one was rated on a scale of 1 to 10.
So in considering the viability of this design, we of course had to consider the competitors we would have. The only competitor on the market that's similar to this product was actually just created in January of 2018. And you can see some screenshots of it there. It's a virtual reality video game for lacrosse goalies. But we identified a few problems that still existed with this game. The major problem with it is that it's a graphic rendering of a lacrosse shooter, and it's not the real thing. So you can't really accurately convey the foot and hip and arm motions of a real shooter that's vital to being able to play goalkeeper and predicting where the shot's going to go. You can't predict that with a rendering of a lacrosse shooter. So the timeline for our construction that we came up with was first, of course, to familiarize ourselves with the Unity program and the coding system that we would be using, which is called C#. Now, neither of us have any coding experience, so taking on a pretty much 100% coding-intensive project was a big thing for us, so we had to learn a lot from online tutorials and things like that. And once we were a little bit familiar, we started with a basic game that would just get the framework of the game down to the basics.
So here we have that basic game, and what you're going to see is the ball go to a random spot on the screen, and then the user just hovers over it and the ball disappears. This was the first step in our prototyping. Then we used that same game and incorporated both a looping feature, so the user can click to restart, as you can see. And after the ball goes to a random spot, whether or not the user is hovering over it, it's a goal or save at that specific time. The times are randomized to simulate randomization of shot speeds. So here's some example code. As we stated, it was C# and Unity. So here you have our final solution in which we incorporated the basic game and the connect. There you have a save, and then it gives instant feedback, such as the other game did, in save or goal.
So in testing our solution, we are not fully tested with the effectiveness of the solution because we wanted to give it more of a long-term testing process where someone might play the game for a week or a month and gauge their improvement. So we haven't had time to do that quite yet. And additionally, connected to that would be to analyze any injuries that were reported and the safety of the product, since of course we want to have a safe product. But considering it's a video game, we anticipate that it would be relatively safe for the users. Some of the other specifications that we tested were that it needed to progress through the shots automatically, and it passed that. And it needed to have multiple shot angles, speeds, and locations, past that. And it also had to be light and compact, which, considering it's a software solution, that's about as compact as you can get. All you need is your laptop and the Kinect sensor. The only specification that it did not pass was that we wanted it to operate in many weather conditions. As you can imagine, the electronic equipment would not do well in the rain or in extreme heat or cold. But we think that since it is a video game, people would most likely be playing it indoors in controlled temperatures and climates, so that shouldn't be something that's too much to worry about.
So along with furthering our testing, we also have some other future plans that include the addition of a start menu, so you can start the game, go through several different game modes, have options, and obviously an exit. We could do shot speeds, random shots, bounce shots, different angles, which are pretty hard. I can't do that. I'm not that skilled. Here's our works cited.
Works cited for the presentation, and we'd like to thank Mr. Condorso, Mr. Love, and Mr. Scott and the PDR and CDR panels for their help along the way in helping us generate the solution, and of course our families and friends and classmates that have made it a good last 4 years for us and helped us out along the way.
Thank you, gentlemen. I'd like to take this opportunity to thank the students one more time. I know Mrs. Zanakis touched on it a little bit about the risks that these students have taken. They've taken on risk in a lot of different ways, but I am most proud of them for the academic risks that they've taken. Part of being part of this program was that they were willing to take the risk to fail at a time in their life when success is critically important. They are trendsetters. They've paved the way not just for Lenape High School, but for all students in the Lenape district by being an inaugural class of the Project Lead the Way program. And they've set the bar nicely high, I would say. So I know there might be some other students in the program that are in the audience here. I'm sure you'll spread the word that the bar has been set and it's high. So it's been inspirational for me to work with them, both their freshman and senior year here. I've learned just as much from them, or maybe more, than I feel they've learned from me, and I'm proud of their accomplishments. Well done. I'd now like to introduce Mr. Joe DeJulius, the Supervisor of Technology Education.
Let's have another round of applause for the students, huh? Phenomenal job. Board of Education members, Dr. Birnbaum, Mr. Catani, The faculty has examined the projects presented by the engineering, design, and development students and hereby certify that they are worthy of acceptance. At this time, it is my pleasure to present the Lenape High School Project Lead the Way class of 2018. Jackson Bauer. Sean Barica. Joseph Cornaglia. Brett Gallagher. Sanjana Jampana. Nathaniel Kim. Jonathan Landis. Zachary Levitt. Andrew Pye. Nivedetha Ramalingam. Keval Tassani. Garrett Williams. And Julia Zack. Another round of applause for all the students, please. Congratulations.